Assalamualaikum warahmatullahi wabarakatuh. Today we will present about our video presentation, which is our topic is spectral line of hydrogens. For our group, we have three members, which is Aiman Hanafi, Hazi Abdullah, and also Arif Azimi, which is me. Okay, now we go to our first topic, which is electronic transition in hydrogen atom. Now let's start with our first topic. From this topic, we know from quantum mechanics, only certain orbits are allowed. Each orbit has a specific energy. For example, orbit number 1 and orbit number 2, they don't have a same energy because for each orbit, they have a specific energy for that orbit. Okay. Electrons closer to the nucleus are lowest in energy, and when the electrons farthest from the nucleus are highest in the energy. So I can say when the electrons close to the nucleus, they have a low in energy, but for when the electrons are so far or farthest from the nucleus, they have a higher in energy than electrons that close to the nucleus. Okay, and in this topic also, we know about ground state and also excited state. What is ground state? Ground state is electrons are in the lowest energy level possible. And for the excited state, if energy is put into the atom, the electrons will jump up in energy, which is the electron move away from the nucleus. It's actually same like a human. When we have a lot of energy, we don't sit down and become a stone. We will be active and we will move away, right? Okay, now we go to the next slide.
Hi, Assalamualaikum. My name is Hazi and I will continue this presentation with second subtopic, which is energy absorbed and emitted in a transition. Firstly, when energy emitted in a transition, nearly all hydrogen atoms are in the ground state at ambient temperature. Multiple atoms can be in excited state at higher temperature or during an electric discharge when there are many collisions between free electron and atoms. When electrons are excited, they can transition from a higher to a lower state, emitting photons in the process. It known as energy emission. Secondly, when energy was absorbed in a transition, the Bohr's model illustrates how photons of just the appropriate wavelength can knock an electron from one energy level to a higher one. Only photon with the correct energy will be absorbed in order to save energy. This explains why a continuous spectrum of light entering a gas will have a dark absorption lines at frequencies corresponding to emission lines. As atom or molecule transition from one energy state to another, they absorb or emit light. The wavelength of the light is related to the energy of the two states by the equation delta E equals to hc divided by lambda, which is Planck constant times speed of light and divided by the wavelength.
Hi, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Aiman Hanafi bin Zaini with student ID 2020495116. Okay, in this slide, I will present to you about Lyman series, Balmer series, and Paschen series. Lyman series is a hydrogen spectral line series that forms when an excited electron comes to the end equal to 1 energy level. And Lyman series is the lowest energy level of the hydrogen atom. The formation of this line series is due to the ultraviolet emission lines of the hydrogen atom. To calculate the Lyman series, we can use Rydberg formula, which is n equal to 2, 3, 4, and next. The difference between Lyman series, Balmer series, and Paschen series, Lyman series is a far ultraviolet and ends at energy level 1. Balmer series. Balmer series is a hydrogen spectral line series that forms when an excited electron comes to the n equal to 2 energy level. Further, this series shows the spectral lines for emissions of the hydrogen atom, and it has several prominent ultraviolet Balmer lines having wavelengths that are shorter than 400 nanometer. Like Lyman series, we can use right-back formula, but Balmer series n equal to 3, 4, 5 and next. The difference between Lyman series and Paschen series, Balmer series is a visible light and different wavelength produce different color of line spectrum. Paschen series. Paschen series is a display when electron transition takes place from a higher energy state to n equal to 3 energy state. Paschen series infrared longer than Balmer and ends at energy level 3.
Okay, now we continue with the self-awareness and also self-responsibility. Okay, now we continue with our topic, which is what will happen if the spectral series are not used in astronomical spectroscopy. Okay, let me tell you what is astronomical spectroscopy. Astronomical spectroscopy is the study of astronomy using the technique of spectroscopy to measure the spectrum of electromagnetic radiation, including visible light. Okay, the classification of the series by the Rydberg formula was important in the development of quantum mechanics. In fact, spectral series are very important to the astronomical spectroscopy because they calculate a redshift and also blue shift using a spectral series, and also they using spectral series to detect presence of hydrogen in our universe and our galaxy. Okay, as you can see in the middle of the circle at our slide, you can see that is a blue shift and also red shift. Okay, now I will explain to you a redshift. A redshift is an increase in the wavelength and corresponding decrease in the frequency and photon energy of electromagnetic radiation, which is light. Okay, now I will continue what will happen. First and all, scientists is able to calculate redshift and also blue shift. It because the terms derived from the color red and blue, which form the extreme of the visible light spectrum. And second, the scientists is able to detect presence of the hydrogen in our galaxy or our universe. Okay, now how we solve this problem? Okay, first, we can use hydrogen spectral series to detect and calculate both of them. Okay, absorption lies in the visible spectrum of a supercluster of distant galaxies, which is a right side on the picture, as compared to absorptions lines in the visible spectrum of the sun, which is left side. And on the picture, arrows indicate a redshift.
Then we should know and aware there is important message why Fraunhofer lines occur in the spectrum of lines. First, it is a solar physics lifeline. Second, the wavelength shift of the absorption line tell us the velocity of the gas, and the depth of the absorption line tell us the temperature. And the last one, there would be no absorption line if the sun was made entirely of pure hydrogen. That's all for me. Thank you. Then we go on to the application or example that shows spectral lines in astronomy. As the title given, astronomical spectroscopy is the application of spectroscopy in astronomy field. Many features of stars and galaxies, including as composition and velocity, are obtained using spectroscopy in this study. Hundreds of small black lines, termed Fraunhofer line, were observed, interspersed among the rainbow of line spectrum. The graph below shows how gases in the sun's outer atmosphere absorb particular wavelength.
And the end of this slide, the conclusion of spectral lines of hydrogen atom. The hydrogen spectrum is an important piece of evidence to show the quantity electronic structure of an atom. The hydrogen atom of the molecule dissociates as soon as an electric discharge is passed through a gaseous hydrogen molecule. The classification of the series by the Rydberg formula was important in the development of quantum mechanics. A spectral line is like a fingerprint that can be used to identify the atoms, elements, or molecules present in a star, galaxy, cloud, or interstellar gas. And that's all from us. Thank you.